Okay, everyone. So for this example, I'm going to do the first derivative test and second derivative test on the same example so we can see kind of some different behaviors when we compare sign charts. So let's start with our first derivative test. So we need f prime, and we're going to need quotient rule, so low d high minus high d low, and that is all over x squared plus 1 squared. Probably going to need to simplify the numerator because we're going to have to find x-intercepts. So this becomes 2x squared plus 2x minus 2x cubed. And I see a mistake that I made. That should be 2x cubed. And this will actually simplify to just 2x over x squared plus 1 squared. So critical points of the derivative. So f prime of x is 2x over x squared plus 1 squared. And I'll need to set my numerator equal to 0. So 2x equals 0, or x equals 0, and my denominator equal to 0. So taking the square root of both sides, x squared plus 1 equals 0, and you should notice that this has no solutions. So we only have an x-intercept for this function. So let's do the sign chart for that. And we'll do 0 in the middle, positive infinity. So at this point, we are going to plug in test points to see whether this will be negative or positive. If I plug in a negative number, I'll have 2 times a negative, and my denominator is going to be positive, and that's because this squared is going to make anything positive, and it's squared again to make it positive. So this will be a negative over a positive, meaning that this will be my negative interval. And we'll do the same thing for the right side, so 2 times a positive number all over a positive number to get me my positive interval. And if you wanted to pick test points and plug them in to check for yourself, that's what you would do. But I'm just using some logic about how square exponents work. If I square a negative number, it's always going to be positive. So there is my sign chart for the first derivative. Let's do the same thing, and let's find the second derivative. So this one might be a little bit more work, but that's all right. And so my second derivative is equal to low d high minus high d low all over low squared. So x squared plus 1 to the 4th. This piece here for the derivative, we would need to use, we are using chain rule, so that's where that all comes from. Let's simplify some more. So we have 2 times x squared plus 1 squared minus 4x squared times x squared plus 1. And there's a reason that I'm not combining or expanding either of those x squared plus 1's. And that is because we can actually reduce some of them. So if you notice here, I have x squared plus 1 to the 4th, x squared plus 1 squared, and x squared plus 1 to the 1st power. So I can actually cancel out one of those, and one of those. And so now, my simplified derivative is going to be 2x squared plus 2 minus 4x squared. That is all over x squared plus 1 cubed. Or to keep it going, negative 2x squared plus 2 x squared plus 1 cubed. So there is my second derivative. So negative 2x squared plus 2 x squared plus 1 cubed. So same thing as before, I need to find my critical points. So I'm going to set my numerator equal to 0. Subtract 2 from both sides. Divide by negative 2. And x squared is equal to 1. So that means I have critical points at x equals 1 and x equals negative 1. And if we see from earlier, we're still not going to have any vertical asymptotes because this is never going to equal 0. All right, so I'm going to copy this sign chart. So this is my sign chart for f prime of x. And right below it, I'm going to make a similar sign chart for the second derivative. So I have values at negative 1 and 1. And we're going to plug in some test points to see if this will be positive or negative. So if I plug in something like negative 2, this is going to be negative 2 times 4 plus 2, and this is going to be over a positive number. So negative 8 plus 2 is still going to be negative, so that means this interval will be below the x-axis. If I plug in something in between negative 1 and 1, like 0, I'm going to get negative 2 times 0 plus 2 over a positive number. And this is going to be a positive over a positive. So that interval will be positive. And then if I plug in something like positive 2, I'm going to get negative 2 times 4 plus 2 all over a positive number, and so this is actually negative as well. So let's talk about our intervals. Sorry, that's the next video. Let's talk about our intervals and split this up. So I'm going to go with this color here, and we're going to split this up. So I have some intervals. I have this interval from negative infinity to negative 1. I have an interval from negative 1 to 0, 0 to negative, or 0 to positive 1, and 1 to infinity. So let's talk about each of these intervals individually. So from negative infinity to negative 1, f of x is concave down, and decreasing. Concave down and decreasing, and that is because the second derivative is less than 0, and the derivative is less than 0. Our next interval, from -1 to 0. F of x is concave up, and decreasing. And that is because f double prime is positive, and the first derivative is negative. So I'm going to pause real quick and think like what that shape might look like. So concave down and decreasing. That means f of x probably looks something like this, where it's concave down and decreasing. So that might be a concave down and decreasing. If I have a concave up and decreasing interval, I may look something like this. Like this is concave up but decreasing. Let's look at our next intervals. So from 0 to 1, f of x is concave up, and increasing. And that is because the second derivative is positive and the first derivative is negative. So concave up and decreasing, or increasing, concave up and increasing, might look something like this, whereas concave up and increasing. And then our last interval, from 1 to infinity. So f of x is concave down, and increasing. And that is because the second derivative is less than 0, and the first derivative is greater than 0. So concave down and increasing might just be the other side of the parabola. So we might have concave down and decreasing. All right. And that is kind of the full analysis of that function f of x. So we could actually use this to sketch out what f of x looks like, is the idea. Is that without graphing, we could actually determine the shape of this graph. And we'll do that at another time, but for now, this is just algebraically how we can determine all that information.